Hi, my name is Gautam Salhotra, and in this video, we present our method Deformable Manipulation from Demonstrations, or DMfD, to solve robotic manipulation tasks on deformable objects. Many everyday tasks use deformable manipulation, such as folding clothes or cooking. The problem is hard due to the difficulty of obtaining object states and predicting their dynamics, especially since environment interaction can change these properties. Furthermore, their complex dynamics and their high-dimensional configuration can increase the task difficulty. Analytical techniques succeed in certain conditions, but fail to generalize with such tasks. We propose a new method, Deformable Manipulation from Demonstrations, or DMfD, for an agent to use experts' data while learning to solve deformable manipulation tasks. It is designed to work with state and image-based observations with both 1D and 2D deformables, and in both simulation and the real world. Now let us look at the DMfD training pipeline. So here we see that the agent obtains observations from the environment during experience collection or the replay buffer during training. For the state-based environments, the observations are encoded by an encoder network. Then the state encoding is passed to the actor and the critic, denoted by the blue and black arrows. Note that the observation for the actor and critic is the same as the state observation. Our method can additionally use image-based observations denoted by red. Here we see that the image observations are cropped and encoded by a CNN. The image encoding is then passed to the actor and the critic denoted by the red arrows. However, for image-based environments, the critic is privileged because it also receives a state encoding while the actor does not. This state encoding can be seen here in the solid black arrow. Specifically, our method uses expert demonstrations in 3 ways. 1, we pre-populate the expert buffer with pre-populate the replay buffer with expert trajectories before training. We leverage an advantage-weighted formulation for the loss function, encouraging the agent to match with the expert actions in the replay buffer. But note that we add an exploration term that we balance with this loss. And finally, we employ reference state initialization probabilistically, where we reset the agent to a state along an expert trajectory. Then we compare the state trajectories of the expert and of the agent to create some sort of imitation reward. Our method has 4 main contributions. First, to encourage wide exploration, we add an exploration term to the advantage-weighted loss. To deploy our method in the real-world settings, we actually extend this framework to the image domain using CNNs and data augmentation. Second, we introduce probabilistic reference state initialization that I just mentioned before. We do this during experience collection, where instead of always resetting the agents to states seen by the expert, as is done in RSI, we invoke this concept probabilistically to promote exploration and learning in states that are difficult to reach. Third, we create 2 new simulation environments for cloth folding with 1 robot arm. We deploy DMfD on a real robot and observe that we have a minimal sim-to-real gap, indicating that it can actually work in real-world settings as well. And finally, DMfD outperforms LFD and non-LFD baselines on both the state and the image-based environments, and for both 1D and 2D deformables. Next, we discuss the results of the image-based environments. So for the straightened rope task, we see that DMfD beats the best baseline with image-based observations. In this rollout, our method solves the task with a clean motion, whereas the best baseline still contains a loop. In the cloth fold image task, an agent must fold a flattened cloth along an edge. We see our method beating the best baseline by folding the cloth with almost complete coverage over the 2 halves. Our new environments that we create are the cloth fold diagonal task that requires the agent to fold a square cloth along a diagonal with only 1 end effector. In the pinned corner version, we successfully fold the cloth almost completely over itself, whereas the best baseline kind of struggles with the task. In the unpinned corner version, we have similar success. And we can see that while the best baseline is able to actually finish the motion, is actually able to fold the cloth, it's not actually able to finish the motion. Here we present a real-world example or a real-world experiment on the cloth fold diagonal task with the unpinned version. But this is a variation with large rotation of the cloth. Our method is also robust to variation in the real world. So we can see these in these rollouts over here. And over the course of all the rollouts we recorded, we have a sim-to-real gap of approximately 6% or so. In conclusion, our method works on the state and image observations and is able to outperform LFT and non-LFT baselines. It is primarily because of the ways in which we use the expert data and balance it with exploration. Additionally, we introduce two challenging cloth fold environments and deploy our system on a real robot. Thank you.